Um, have you ever been staring at a really stubborn screw?
Oh, definitely.
Right. And you realize you don't have a screwdriver anywhere nearby, and you think, you know what? This butter knife will do just fine.
Yeah, we have all been there. It actually works, like, in a pinch.
It does.
Yeah.
Wedge the tip of the knife into the slot, you turn it carefully, and the screw moves.
Yeah.
But push just a little too hard on a screw that's, rusted in place, and you bend the knife.
Yeah, because it simply wasn't built for that kind of twisting pressure.
Exactly. And in the high-stakes manufacturing world, professional machine shops do this all the time.
They really do.
But instead of a butter knife, they're trying to mill solid steel using these lightweight, incredibly fast machines known as tapping centers.
Which is wild because pushing a specialized lightweight machine into a solid block of dense steel risks a lot more than just, a piece of ruined silverware.
Oh, absolutely.
I mean, when a tool bends or snaps inside a machine spindle running at tens of thousands of revolutions per minute, you are looking at catastrophic hardware failure and incredibly expensive downtime.
Right. So, welcome to our deep dive into the mechanical boundaries of manufacturing.
Glad to be here.
Okay, let's unpack this. Our mission today is to take you through a fascinating set of technical guidelines that dictate whether a lightweight tapping center can actually survive milling tough steel workpieces.
It is a delicate balance.
It really is. We're going to uncover the exact physical limits of this equipment, dive into the actual physics of cutting metal, and look at how clever process optimization allows operators to temporarily cheat a machine's physical boundaries.
Because it's not just about factory floor guidelines.
Right. It is basically a master class in understanding the absolute limits of the tools we use.
Absolutely.
So let's start with the machine itself. Why are tapping centers so notoriously bad at handling steel?
Well, the limitation is built directly into the machine's anatomy, specifically the spindle.
The butter knife itself.
Exactly. Tapping centers typically use what is known as a BT30 spindle, and these are engineered almost exclusively for extreme speed and rapid acceleration.
Okay, how fast are we talking?
We are talking about rotational speeds up to, 24,000 revolutions per minute?
Oh, wow.
Yeah, that speed is incredible if you are machining soft, non-ferrous metals.
Like aluminum alloys or copper, right?
Right, where the tool can just zip through the material like a hot knife through butter. But the motors driving these spindles are, they're small.
Really small.
Yeah, they usually max out around 5.5 kilowatts of power.
So speed doesn't necessarily equal power.
Not at all.
It's kind of like trying to tow a heavy boat with a high-revving sports car.
That is a great way to put it.
I mean, the sports car can easily hit 24,000 RPM on an open track, but it just lacks the low-end torque of a truck to pull dead weight.
Exactly. The motor windings in a high-speed spindle are optimized for frequency, not magnetic leverage.
So what happens when you hit steel?
Well, when you push a cutting tool into solid steel, the material fights back with massive shear resistance. And because the BT30 spindle lacks that heavy torque,
It stalls.
yeah, the motor can easily stall. The spindle just stops spinning while the machine is still, trying to push the tool forward into the metal block.
Oh, that sounds bad.
It is. The tool snaps, gets embedded in the steel, and ruins the entire part.
Wait, what happens to the machine itself during a stall like that? I'd imagine that sudden halt sends an incredible amount of stress back up into the machine.
It does. It generates a massive thermal overload. I mean, even when the spindle doesn't completely stall, continuous heavy cutting in steel forces the motor to run at its absolute maximum electrical draw.
And all that energy has to go somewhere.
Right. All that electrical energy fighting mechanical resistance turns directly into heat.
Wow.
And spindle bearings are these super precision components. They often use ceramic balls that rely on a microscopically thin layer of specialized bearing grease to survive spinning at 24,000 RPM.
So the heat just destroys the grease.
Exactly. When the spindle is struggling against dense steel, the thermal load spikes. The housing expands, tolerances tighten, and that delicate grease literally cooks and degrades.
That is wild. And our sources mention that a specific standard procedure called rigid tapping basically fails completely for internal holes larger than a size M6 on these machines.
Yeah, that's a hard limit.
So what is rigid tapping, and why is that M6 size the absolute breaking point?
Well, rigid tapping is the traditional way to cut internal screw threads into a drilled hole.
No.
The machine forces a threaded cutting tool, which is called a tap, straight down into the hole, and it synchronizes the downward feed with the rotation of the spindle.
So it's plunging straight in.
Right. And the problem there is surface contact. As the tap goes deeper, more of its cutting teeth engage with the solid steel all at the exact same time.
Oh, I see.
Yeah, so by the time you reach an M6 thread size, which is roughly a 1/4 inch across, the amount of steel gripping the tool demands more torque than that tiny 5.5 kilowatt motor can physically provide.
So the resistance just overcomes the spindle's magnetic field.
Exactly, and it stalls.
Okay, so if rigid tapping destroys the machine or stalls the motor, how do these shops get threaded holes into the steel parts they're actually working on? I mean, if they know it's going to fail above an M6 size, why do machine shops even try it? Are they just hoping the machine won't notice the resistance?
Well, what's fascinating here is that shops often push these limits just to save time. It is this constant clash between desired speed and physical reality. But when they know it will fail, they abandon that plunge and cut method entirely.
Oh, okay. So what do they do instead?
They switch to a technique called thread milling.
Thread milling.
Yeah. Instead of a tap that engages all the steel at once, a thread mill is a much smaller tool. It drops into the hole and uses these circular sweeping motions to slowly carve the threads into the sidewall.
Oh, wow. So it bypasses the machine's lack of raw torque by taking a completely different path.
Right, a much lower resistance path. It takes longer, but it keeps the spindle alive.
Okay, so that solves the issue for cutting threads. But what about carving the external shape of the steel part itself?
That's where things get tricky.
Right, because we can't magically turn our sports car into a tow truck. We can't change the spindle's power output.
Nope.
So that means we basically have to put this machine on a strict material diet. I mean, the sources draw a very firm line in the sand regarding the type of steel allowed,
They do. You have to keep it below HRC 30.
the Rockwell hardness scale.
Exactly. The Rockwell scale is the ultimate arbiter here. HRC 30 is the absolute ceiling for tapping center.
So that restricts operators to mild carbon steels.
Right, like 1018 or standard A3 steel. And ideally, you want thin-walled parts.
Because mild steels have a softer internal grain structure, right?
Yeah. When the cutting edge of the tool hits the metal, the mild steel yields and shears away with relatively low cutting resistance.
So the weak spindle can maintain its rotation without drawing too much electrical current. Okay, here's where it gets really interesting. HRC 30 limits us to mild carbon steel. But wait, so I accidentally put an HRC 50 mold cavity into this lightweight machine, or a block of HRC 40 tool steel. It's not just that it cuts badly or makes a loud noise.
No.
It actually, permanently destroys the machine's skeleton.
Yes, it results in permanent structural deformation.
Wow.
To understand why, you have to look at how different machines are built to absorb vibration.
Okay.
Heavy-duty vertical machining centers are built with cast iron boxways.
Boxways.
Yeah, these are thick, incredibly dense, solid metal tracks that the moving parts slide on, and cast iron has natural friction dampening properties.
So when a tool violently slams into hardened steel on one of those heavy machines,
The massive shock waves are absorbed and dissipated by the sheer mass of the cast iron.
but tapping centers don't use boxways.
Nope, they use linear guide rails.
Are linear guide rails designed differently, to prioritize speed over strength?
Completely different mechanisms. A linear guide rail features a block that glides over a thin steel rail using hundreds of tiny, recirculating ball bearings.
Oh, ball bearings.
Right. It operates on rolling friction, which allows the machine to zip back and forth at lightning speeds with almost zero resistance.
But those tiny ball bearings must have an incredibly small point of contact with the rail.
Exactly.
So when that heavy shock wave from cutting, say, HRC 50 steel travels up the tool and into the machine structure,
It focuses all of that violent kinetic energy directly onto those tiny points of contact inside the guide rails.
oh, it sounds awful.
It is. The technical term for what happens next is Brunelling.
Brainily.
Yeah. The shock literally causes the ball bearings to dent the steel track. They press these microscopic divots right into the rails.
That is brutal.
And once the rails are pitted, the machine permanently loses its smooth motion and precision.
You have effectively vibrated the machine's skeleton out of alignment.
Yeah, and replacing those guide rails is a devastatingly expensive repair bill.
So the skeleton gets dented from the inside out. That is a very powerful reason to stick to mild carbon steel.
Absolutely.
But, even assuming we stay below that HRC 30 safety limit, the tapping machine is still physically weak.
Very much so.
To prevent the machine from just shaking itself to pieces with awful surface chatter marks, those nasty vibration patterns left on the metal, the shop has to alter its milling strategy completely.
Right. Process optimization becomes the only way to succeed.
So they have to compensate for the limited rigidity.
Yes. You have to change how the tool interacts with the metal.
Yeah.
For instance, using large cutting tools is just impossible.
Like a 50-millimeter face mill.
Yeah, a standard 50-millimeter face mill requires massive horsepower to push through solid steel because the cutting edge spans such a wide arc.
Right.
The pushing force alone would trigger structural vibrations that the linear rails just cannot handle.
So the sources mandate shrinking the tools down drastically. They specify small diameter end mills, like under 20 millimeters. And they also note these smaller tools need to have high helix angles.
Yes, the geometry of the tool is just as important as the size. A high helix angle means the flutes, the cutting edges, wrap around the cylindrical body of the tool much more tightly.
Like a steep spiral staircase.
Exactly. When a standard, straight fluted tool hits metal, the entire length of the cutting edge smashes into the steel at the exact same millisecond.
Ouch.
Yeah, that creates a massive spike in radial force, which just pushes sideways against the spindle.
I see. So it's basically the difference between trying to chop down a tree with one giant heavy swing of an axe
Right.
versus using a pocket knife to whittle it down with 1,000 tiny, fast, strategic slices.
That is the perfect analogy. The high helix geometry physically converts a lot of that violent sideways radial force into upward axial force.
Oh, wow.
It directs the pressure up into the spindle bearings, which are actually designed to handle thrust, rather than pushing the tool sideways and bending it.
That makes so much sense. But because you are essentially whittling the metal, the parameters of the cut must be severely restricted.
Very restricted. Operators cannot program deep cuts. The depth of the tool's engagement into the steel is limited to 2.8 millimeters maximum.
2.0 millimeters, and for precise jobs.
For high precision finishes, they might only take like 0.2 millimeters of material per pass.
Wow, 0.2 millimeters. But wait, if the tool is smaller and taking microscopic cuts, wouldn't the instinct be to crank the spindle speed up to 24,000 RPM just to get the job finished quickly?
You'd think so, but doing that would instantly destroy the cutting tool.
Really?
Yeah, even taking shallow cuts, shearing steel generates incredible friction. When you spin a tool at 24,000 RPM against steel, the friction at the cutting edge creates a massive thermal overload.
Oh, because the heat can't dissipate fast enough.
Exactly. It concentrates on the tool's carbide edges, literally burning them away or causing them to chip.
Do you have to slow it down?
To manage the thermal load, spindle speeds must drop drastically from the typical 12,000 RPM used for aluminum, down to somewhere between 3,000 and 6,000 RPM for steel.
That sounds incredibly slow. I mean, if you were taking 0.2 millimeter cuts at just 3,000 RPM, how does a modern machine shop program all these tiny, slow passes without just bleeding money on labor and machine time?
Well, this is where software algorithms step in to save the hardware. Machine shops rely on modern dynamic milling software to generate these tool paths.
Okay, dynamic milling.
Yeah, the software algorithms fundamentally change how the tool travels through the material. Historically, a programmer would just draw a straight line through a corner, right?
And force the tool to plow directly into the metal.
Exactly. But the software now utilizes trochoidal milling.
Trochoidal milling.
Yes, meaning the tool path looks like a series of overlapping loops or circles.
So the software is actively altering the tool's path to control the physical forces happening at the cutting edge.
Exactly. It calculates exactly how much of the tool is engaged in the metal at any given microsecond. This is called controlling the angle of engagement. If the tool approaches an inside corner where it would normally get buried in steel and experience a massive spike in resistance,
It changes path.
right, the software forces the machine to loop outward, taking progressive, sweeping circular bites, so it maintains a perfectly constant load on the spindle.
That is brilliant. The tool never bites off more material than the weak 5.5 kilowatt motor can handle.
Never.
Our sources also mention radial chip thinning in these dynamic milling algorithms. What's that about?
Oh, that's crucial. When you take extremely shallow cuts, like those 0.2 millimeter passes we talked about, the actual piece of metal being shaved off, the chip, is significantly thinner than the distance the tool moves forward.
Okay.
And a thin chip cannot absorb heat.
Oh, I see.
So the algorithm automatically calculates this and dramatically increases the feed rate, which is the speed the tool physically moves across the part.
So it's moving across the part really fast, even though the spindle speed is low.
Exactly. The tool races through those shallow cuts fast enough that the heat generated by friction is transferred entirely into the flying metal chip.
Wow.
Yeah, rather than soaking into the tool or the spindle itself. If we connect this to the bigger picture, these algorithmic tool paths from dynamic milling software act as a bridge. They allow weak hardware to survive by outsmarting the physical resistance of the material.
Okay, but given the razor-thin margins for error you just laid out, I mean, having to buy specific mild steel, dropping speeds to avoid burning tools, relying on complex dynamic milling algorithms just to avoid denting the linear guide rails.
That's a lot.
It is. So what does this all mean for the people running these shops? Is this entirely a math equation for them, calculating the risk of a ruined spindle versus the cost of buying a dedicated heavy machine? Why hasn't the industry just banned tapping centers from cutting steel entirely?
It all comes down to the brutal economics of setup time. The sources actually draw a very clear boundary for when this compromise makes business sense.
Okay, when is it worth it?
Tapping centers should really only be used for steel during occasional small batch runs. We are talking about orders of fewer than 200 pieces.
Ah, okay. So if a part requires, say, 30 small holes drilled into it, the tapping center is naturally going to excel at that specific task.
Right, because of its high-speed spindle. The tapping center features incredibly rapid tool changers. It can swap a drill bit for a tap in fractions of a second.
That's amazing.
So if a batch of parts needs a massive amount of drilling and only a few minor flat surfaces milled out,
It's far more efficient to just keep the part inside the tapping center.
exactly, moving 150 parts to a completely different, heavier machine just to shave a few millimeters of steel off the top costs hours of labor and machine setup time.
That makes total sense. So operators will just accept a slower, highly optimized dynamic milling pass to finish the part without having to move it.
Exactly. And the sources also point out the use of oil mist sprayers. During these specialized steel runs, operators add continuous oil mist to the cutting zone, providing necessary lubrication to assist the tool against that intense friction.
Right. But what about for larger operations?
Oh, any factory doing regular, continuous heavy steel processing or carving out large hardened mold cavities, they must abandon the tapping center.
The risks are just too high.
Way too high. The sheer volume of material removal will degrade the machine rapidly, regardless of any software optimization.
Because at a certain point, physics always wins.
Exactly. Those operations require the mass and rigidity of a heavy vertical machining center equipped with cast iron boxways.
Like you mentioned earlier.
Right. I mean, a second-hand, older boxway machine will outperform and outlast a brand new tapping center when it comes to plowing through dense steel day in and day out.
Wow. Okay, so to wrap up our deep dive today.
Yeah.
Yes, a lightweight tapping center can mill steel, but it is a delicate high-wire act of engineering.
It really is.
To pull it off without permanently destroying the equipment, shops must enforce strict physical boundaries. The steel must be mild carbon, kept below HRC 30 on the Rockwell scale.
Crucial.
And the cutting tools must shrink to under 20 millimeters and utilize high helix angles to redirect forces. Cuts must remain razor thin, under 2 millimeters deep.
Yep.
And finally, advanced dynamic milling software must take the wheel, calculating constant chip loads and trochoidal tool paths to protect the machine's fragile linear guide rails from catastrophic damage.
Right, because the tapping center is fundamentally a specialized instrument. Using it outside of its primary design demands a deep understanding of physics, friction, and kinetic energy. Knowledge is most valuable when it's applied safely.
So the next time you find yourself trying to force a tool to do something it wasn't originally designed for, whether that tool is a complex software program you are trying to bend to a new workflow, a management framework you're applying to a creative team, or even a literal physical tool in your garage, remember the tapping center.
That's a great takeaway.
You can bend the rules through careful optimization. You can achieve temporary success. But you must deeply respect and understand the underlying physical boundaries of your system before you break it entirely.
And in this deep dive, we saw how